Beyond our solar system isn't empty. It's frontier country. Past Pluto, the sun's influence fades at the heliopause, where the solar wind gives way to the galaxy. Beyond that is interstellar space, thin gas, tangled magnetic fields, rogue planets, and ancient comets cruising the dark. We'll map the nearby neighborhoods, the Kuiper Belt, the distant Oort cloud, and the local interstellar cloud we're moving through. Then see how nearby stars, dead stellar remnants, and the Milky Way's tides shape our sky. If "out there" sounds like nothingness to you, this will change your map of home. Come on, let's step off the solar shore. Let's start with tides. On Earth, the moon pulls on our oceans and makes bulges. Now scale that up to galaxies. When two galaxies drift close, their gravity reaches across space and tugs on each other's disks. The result? Huge tides that stretch spiral arms into bright bridges and long, elegant tails. You can picture stars and gas getting pulled into shimmering streams as the disks warp and twist. No magic, just gravity doing steady, predictable work on a massive scale. So do stars actually crash into each other? Almost never. Space is unbelievably empty. Even during a collision, individual stars usually pass by untouched. For scale, if the sun were a grain of sand in New York, the nearest star would be another grain in Chicago. Think of two swarms of fireflies drifting past each other. Lots of near misses, almost no hits. Gravity shapes the crowd, but direct star-star impacts are vanishingly rare. Gas and dust play by different rules. Stars are tiny points. Gas clouds are huge and spread out across light years. They can't just slip past. They feel drag and get compressed, and they launch shockwaves. Where big clouds slam together, pressure rises. The gas collapses under gravity, and starburst regions light up. New clusters flare into being. The biggest newborn stars live fast and explode as supernovae, stirring and sculpting glowing nebulae. It's a stellar nursery plus fireworks. At the centers of most large galaxies sit supermassive black holes, millions to billions of solar masses. As their galaxies interpenetrate, those giants feel a kind of cosmic break called dynamical friction. It's a gravitational drag from the surrounding stars and dark matter that saps their motion. The pair sinks toward the new shared center. For a while, you can get two blazing cores, dual active galactic nuclei, each feeding on a hot, spinning disk and shining across the universe. Much later, hundreds of millions of years after the merger, the black holes tighten into a close binary. They orbit, faster and closer, and bleed energy as gravitational waves, ripples in space-time itself. The loss is relentless. They spiral in and likely merge in a final, violent burst of those waves. No math tonight, just the idea that their finale leaves a mark on the fabric of the universe. Meanwhile, billions of individual stars get their lives scrambled. Calm, circular orbits become stretched and eccentric. The push and pull carves out shells and long tidal streams. Ghostly ribbons of stars that wrap around the remnant. Star clusters wander too. Some get kicked into the galaxy's halo, others sink toward the messy new center. Order gives way to a wilder mix. Through all of this, dark matter sets the stage. Think of dark matter halos as giant, invisible cocoons, far bigger and more massive than the galaxies they hold. They're the first parts to interact, and their gravity steers the whole encounter. They soak up and redistribute energy like a vast shock absorber. If you want to predict the dance, follow the dark matter. These encounters rarely end in one dramatic pass. More often, the galaxies sweep through, separate, and get pulled back for another round. Each pass strips more material, sparks fresh starbursts, and tightens the embrace. It's gradual assimilation, not a single crash, more like traffic merging lane by lane than a sudden pileup. The timescales are epic. A first pass with long tidal tails can play out over tens of millions of years, but the full coalescence, from first approach to a calm remnant, often takes hundreds of millions to a few billion years. It's choreography you only appreciate in time-lapse, with gravity keeping steady time the whole way. Zoom in, and the details pop. Lanes of gas and dust twist into bright knots where stars are forming. Dark filaments mark shock fronts where clouds collide. Fresh blue star clusters flicker on, then fade over millions of years. It looks chaotic, but the rules are simple. Gravity pulls, pressure pushes back, and radiation from newborn stars clears and heats the gas. After a few 100 million years, the frenzy cools. The cold gas, the fuel for new stars, gets used up or heated and blown out by supernovae. Star formation drops. The former spirals, now thoroughly mixed, settle into a rounder, more uniform system, often an elliptical galaxy, older, redder, and short on the cold clouds needed to spark new suns. Even when the big show ends, the remnant keeps faint scars. With deep images, astronomers find clues, dim tidal tails, ghostly loops, delicate shells tracing the outer halo. From those patterns, they can reconstruct the story, who merged, how massive they were, the directions they came from, and roughly when it happened. This isn't just theory, we see it. The Antennae galaxies are a classic, with intense starbursts and tangled dust, captured by Hubble and the James Webb Space Telescope. The Mice galaxies show those dramatic tidal tails, stretching for hundreds of thousands of light years. These snapshots match our models and reveal the messy, beautiful reality of galactic change. Our own future fits the script. The Milky Way and Andromeda are on course to merge in about 4.5 billion years. The odds of the Sun hitting another star are tiny, but our whole solar system will likely shift into a new, sweeping orbit. For anyone watching from a future Earth, the sky will evolve. Andromeda swelling huge, then two bright cores circle in a long, slow duet. Quick recap. 1. Gravity raises galaxy-wide tides that pull out bridges and tails. 2. Stars almost never collide, space is just too big. 3. Gas clouds do collide, making shocks and starbursts that fade as fuel runs out. 4. The central supermassive black holes sink inward, pair up, and much later, merge in gravitational waves. 5. Stellar orbits get scrambled, building shells and streams around the remnant. 6. Dark matter halos are the quiet puppeteers, steering and soaking up energy. 7. The story unfolds over many passes, hundreds of millions to a few billion years, before the final settle. 8. The usual outcome is a larger, smoother galaxy, elliptical or lenticular. Spiral arms fade, dust lanes thin out, and with cold gas gone, major star formation shuts down. Not a wreck, it's a reorganization into a more mature state. Think of it like an orchestra. Dark matter sets the tempo, gravity carries the main melody, colliding gas clouds add the big crescendos, the pairing black holes bring the deep final hit. When galaxies meet, the score swells, yet the instruments themselves almost never collide. Perspective matters. From far away, you see grand structure, tails unfurling, cores converging, a silent ballet. From inside, for anyone living there, it's slow, constellations drift, new rivers of stars rise, gentle gravitational nudges build over ages. Both views are true, just different seats in the same theater. So what happens when galaxies collide? It's a process, not a crash. Tides reshape them, gas ignites, black holes meet, and over eons the chaos settles into something larger and quieter. Often, a serene elliptical remains, its light a blend of countless stars, its structure holding the memory of the encounter. Look up and remember, the universe prefers dances to wrecks.